Hey everyone! We're going to talk about the efficiency of linear search versus binary search. So really quickly, I'll remind you of the algorithm to linear search. So all we really do is we loop through all of the elements of a list until we find the one we're looking for. So the thing about linear search is there's no prerequisite for the list. The list could be sorted or unsorted. We don't know. And so in the worst case, we're looking for the last element of the list. And in that case, we have to loop through every single other element until we find it. So in this first list, the worst case would be when we're looking for 8, and in the second list, it would be when we're looking for 6. And again, we don't know anything about the list. We don't know that the first one is sorted. And so in the worst case, the big O of linear search is O of n, because we have to loop through every single element in the list. And n is the length of the list. So if we have a list with 1,000,000 elements in it, and we happen to be searching for the last element in that list, that becomes pretty costly. So we have binary search. And binary search assumes that the list is sorted before you start. And that will probably take O of n log n if you're using a merge sort or something like that, which is about as good as you can do when you're sorting a list. But once you have this sorted list, what we do is we look for the middle element. So we take the length of the list and divide it by 2. And in this case, that will be 4. And we go to that index. So at index 4, we have 5. And we compare the element we're looking for the element at the middle. Now, if the element we're looking for is smaller than the element in the middle, we know that we only have to look in the first half of the list. But if it's bigger, then we look in the second half of the list. And you see that every time we do this, we actually split the list in half, and we cut down the elements that we could possibly be looking at in half every single time. And we see also that we cut it down, and whenever we cut it down, we very quickly get down to singleton elements, and so we're really quickly going to converge onto the exact element that we're looking for. For example, if we're looking for 1, the first thing we do is we say, okay, the middle of the list is 5, but we're looking for 1, and 1 is smaller than 5, so that means that we look at the first half of the list. And so then we go here, and we say, okay, the middle of this list is 3, 1 is smaller than 3, so we're going to look at the first half of this smaller list. So we go here, and we say, okay, the middle of this list is 2, but we are looking for 1, and 1 is smaller than 2, so we're going to look at the first half of this list. And now we have 1, and there are no other elements in this list, so we found it. And we can see that this is actually a function of the log base 2 of the length of the list. And so whenever we cut down a list in half, it takes log base 2 steps to get down to singleton elements. So for example, this list has 8 things in it, and the log base 2 of 8 is 3, and we can actually see that, yes, it takes 3 steps to get down to singleton elements. And so when we actually search the list, it only takes log of n time to search it, because that's how many steps we sort of have to take before we converge onto singleton elements, which is really cool. And so that's why binary search is a lot faster than linear search.